Hi there. Today is going to be just a short lecture with two more examples on related rates. Okay, so the idea is to not just memorize the examples, there's too many to go through, but the idea is to understand what you need to do so that given some new example or some new question that you haven't seen before, you know what to do. Okay, so please go through the tutorials with the practice problems so that you get an idea of what you can do for some unseen problem. Okay, but for now we're just going to be going through two more examples on related rates. So number one. Okay, so suppose that we have two resistors, R1 and R2 connected in parallel. Okay, so what we want to do is determine the rate of change of the total resistance. So the total resistance, if R1 is increasing, so if R1 is increasing at a rate of 0.4 ohms per minute, and R2 is decreasing at a rate of 0.7 ohms per minute. Okay, given R1 is equal to 80 ohms and R2 is equal to 105 ohms. Okay, so we know that R1 is increasing at this rate, R2 is decreasing at this rate. We know the values at some time. We want to know the rate of change of the total resistance given these parts of the total resistance. Okay, so we start off with the equation that relates all of this, and that's going to be the total resistance. So, 1 over R is equal to 1 over R1 plus 1 over R2. Okay, so that's the equation relating all of these resistances together. Now, you don't need to know this. This will be given. Okay, but I think you have done it in your matric work. So what we want to do is start with this equation and then find the rates of change that we need. So we need the rates of change of the total resistance as well as the rates of change of the individual resistances. So let's do d by dt on both sides. Okay, exactly what we did before. So that's d by dt 1 over r1 plus 1 over r2. Now we know that capital R, that's a function of time, R1, that's a function of time, and R2, that's a function of time, so we're going to have to use the chain rule. So here we get minus 1 over R squared, dr by dt. Let's just put that in red, that's the thing we want. Okay, this is equal to minus 1 over R1 squared, dr1 by dt, minus 1 over R2 squared, dr2 by dt. And just a note, here we use the chain rule. Right, because they are functions of time. Okay, we can get rid of the minus signs. So here we can get rid of all of those. We can take the r squared over. So we get dr by dt, which is what we want, is r squared into 1 over r1 squared, dr1 by dt, plus 1 over r2 squared, dr2 by dt. Now we know R1, we know R2, and we know the respective rates of change, but R we don't know. That's not given. But we know the individual resistances, so we can calculate what the total resistance is. So recall, 1 over R is equal to 1 over R1 plus 1 over R2. So 1 over R is equal to 1 over 80 plus 1 over 105. We can do a bit of rearranging, and we end up with R is equal to 45.4 ohms. And a quick little check, the total resistance should always be smaller than the smallest resistance. So the smallest resistance here is 80, so the total resistance being 45.4, that's a good sign that we got the answer correct. If your total resistance is more than the smallest resistance, you've done something wrong there. Okay, so just a quick little check to see if we're right. Okay, so we can take this, substitute it into the previous equation that we found, and then we can solve. So dr by dt, that's going to be r squared. We know what that is now. That's 45.4 squared. Then it's going to be 1 over r1 squared, so that's 1 over 80 squared. Then dr1 by dt, we know what that is. R1 is increasing at a rate of 0.4, so that's going to be 0.4, plus 1 over R2 squared, so that's 1 over 105 squared, and then dr2 by dt, we see here R2 is decreasing at a rate of 0.7, so dr2 by dt is minus 0.7, because it's decreasing. Okay, and then we can just simplify this, and we end up with minus 0.002 ohms per minute. Per minute. Okay, so that is the rate at which the total resistance is decreasing. So the total resistance is decreasing because of the negative. Okay, that's because of this negative sign at a rate of 0.002 ohms per minute. Okay, so you see that the total resistance is decreasing, again because of that negative sign. Okay, let's have a look at another example. So the last example for today. The sides of an equilateral triangle are decreasing at a rate of 3 centimeters per minute. Okay, how fast is the area decreasing when the side length is 10 centimeters? Okay, again we've got this related rate. So we want to know how fast the area is decreasing, so that's one of the rates, and we know that the side length is decreasing, so that's the other rate, and we want to know how are they related to each other. So let's start off with how the area and the side length are related. So a quick little sketch of an equilateral triangle, side length S, this angle that's 60 degrees, or pi over 3 radians. Okay, so the area, again, half base times height, so that's half times S times root 3 over 2S. So we can simplify that as root 3 over 4S squared. Okay, so that's the area Now we want to find the rates of change, so we need to do the time derivative on both sides. So d by dt of a is d by dt of root 3 over 4s squared. Now a, that's a function of t, and s, that is also a function of t, so we're going to end up with dA by dt is equal to root 3 over 2 times s ds by dt, again, the chain rule. Okay, so if you want to write this out a bit more explicitly, we have s of t inside squared. Okay, so that's why we need the chain rule. We've got this outside function, something squared. We've got this inside function, s of t. When we do the chain rule, we differentiate the outside, so the 2 came down, and then we differentiate the inside, so it becomes ds by dt. Okay, now we've got the two rates of change that we're interested in, so we can find dA by dt in terms of the other. So dA by dt will be root 3 over 2. The side length was 10, and the rate of change, that was decreasing at a rate of 3 centimeters per minute. So that's going to be a minus 3. So we end up with a minus 30 over 2, so minus 15. So minus 15 root 3 centimeters squared per minute. Okay, so that is the rate of change of the area in terms of the rate of change of the side length. Okay, so this is fairly similar to one of the tutorial problems, finding the rate of change of the area given the change in the side length or given the change in one of the interior angles. Okay, so please have a look at that tutorial problem if you want some more practice with these shape type problems. Okay, so that's going to be it for today. If you do have any more questions on rates of change or related rates, please look through the notes, or you can send me an email. I'll be happy to help you out. Okay. Also, the tutors are available, so please ask them for help as well if you need assistance. Okay, so the tutorial solutions are available as well, but please try and do them before looking at the solutions. Okay, the reason being is if you just look at the solutions without trying them, you might think that you could answer it because the solutions look obvious. However, in a test type situation, you might be stressed out and all that, and it might not be so obvious in that case. Okay, so please try it out. If you really don't know what the answer should be, then you can have a look at the solutions. But first, try it out before you look at the solutions. Okay, just a bit of advice on that. Okay, but yeah, please, if you have any questions, just send me an email and I can help you out. Okay, I have been getting some emails from students, so that's good to see. Hopefully we do get back to in-person lectures. Okay, but I have been seeing emails, so that's good. I can see some students are still doing the work. Okay, so please send me questions if you have, send the tutors questions if you have as well. Okay, I'll see you next time.